I thought I would use this opportunity to tell you guys a bit about high-level software architecture concepts. So this is not thinking of the creation of software at the level of coding, arguably not even at the level of engineering anymore. This is about the overall big picture architectural design. Um, Here's a picture of the architect from The Matrix. This is the place where Neo finally meets his creator, and he discovers he is necessary because the system is using formal logic, and Gödel's theorem says there is always this weird thing that can't be proved or understood by the machine, so you must have a human intervention to answer that question. And so here's Neo finding out the meaning of his existence as a resolution of Gödel's theorem in The Matrix. If you come back and study logic and computation, you'll learn a whole lot about that. But the architect is based on a modern concept of a software architect. He is the creator of The Matrix. He's the overall designer of all the software making up that system. As you can see, he's very, very powerful. He's the main person in charge of all of this stuff. He can clearly afford to buy lots of nice TVs and a big fancy chair, which you could also do if you become a software architect. So this is clearly a nice role for more experienced software creators to move into. It's a nice thing to do in your career when you burn out of being a programmer and you want to move up and become a little more big picture. It's often combined with managing other people who you then get to go out and write the code for you. The role is very much analogous to a physical architect. So as in designing a building, you bring in the physical architect to do the big picture stuff, often quite an artistic kind of role, but also making the initial design, the big picture design, before you bring in the engineers to check that design out and make sure the thing isn't going to fall over. So I've got a couple of topics to talk about at this level. Maybe this is going to go over the next 2 weeks. There's quite a lot of this stuff. Let's see how we get on. How many questions are being asked? I'm going to start by talking about a concept called design patterns, which is roughly a bunch of kind of best practice ideas. They're little tricks and simple machines that get used in a whole load of software and are passed on from one generation of software architects to the next because they're useful to know about. And maybe later on we'll talk about refactoring, which is how you change your design during the course of a project rather than having to design everything up front. So probably for today we will talk about design patterns. Has anyone come across these before at all?
Yes.
Okay, anyone else? Okay, so the concept of design patterns has been around for a long time now. Software books don't often stick around for long periods, but this is an unusual case. This is the Design Patterns book from 1994. It's almost always referred to as the Gang of Four book. It has 4 authors, and those authors are also known as the Gang of Four. They used to travel around doing a road show. You could go and see the Gang of Four live performance. So it was very tied up with 1990s style object-oriented programming at the time. Maybe some of that is a little dated now. We'll talk about some of the criticisms and controversies around this stuff too. But a lot of it is still in use in various ways. It has stood the test of time. So the concept of a design pattern then is that it is distilled wisdom about software architecture. Software architects find themselves solving the same little problems again and again in different contexts. And there have evolved these very standard ways of both recognizing those patterns. Giving them a name is very important. When you name something, then you can control it. Once you recognize it and have a name, then you can have these standard methods for addressing those problems and for fixing them. Okay, now design patterns are distinct from other forms of software creation wisdom. For example, you will get wisdom around the coding level of software creation. This is ideas like structured programming, things like coding standards. We're not talking about the code level here. We're talking about the big picture architecture, which basically means the structure of the classes and objects and the interactions between them in an object-oriented language, or similar kinds of structures and interactions in other languages. So the concept is based on an analogy to what are known as simple machines. Anyone seen these before? Okay, these are from mechanical engineering. So for I think hundreds of years now, mechanical engineers have studied and taught one another using this fairly standard collection of simple machines. Things like a lever, things like a pulley. You can see all these ingenious small subcomponents of a larger machine that are known as simple machines. And the idea is that by studying these standard patterns in mechanical engineering, you're now equipped with a toolbox of ideas when you need to go off and create a big complex machine. Now, instead of building that machine just out of nuts and bolts, you can now build it out of these simple machines. If we have any Lego fans here, there are very analogous ideas in Lego. There are standard ways of putting a few bricks together to make a thing, and then you build your big building out of those patterns. If we have any musicians here, there are similar ideas. You might have standard chord sequences, standard little musical licks that you combine together to make a solo. So they're the basic building blocks. You've seen this idea before in computer architecture. So here's a fun one. Who can remember what these are? These are what I taught you last year. These are 3 simple machines built out of digital logic.
The one on the right is an adder.
Is it a full adder at the bottom?
Correct. What kind of adder?
It's a half adder, isn't it?
It's a full adder, actually. It's made out of 2 half adders. You can see the repeated structure. Okay.
Oh yeah, no, because it's got double X.
So,
yeah, okay.
Yeah, two half adders make a full adder. So we also saw a decoder. This is a thing which takes a binary encoding of a decimal number, say. So here's a 3-bit number coming in, and it converts it to a physical selection of 1 of 8 physical lines coming out. And this one's a shifter. If you turn on the shift signal, it will shift all the bits along by 1. So we've already seen this idea. This is used very commonly in hardware. This is the same idea now being applied to software architecture. Software architecture is a completely different thing from hardware architecture, by the way. They just happen to have the same word in it. So where do these design patterns come from? For a long time, they were just passed on from one programmer architect to another as a kind of trade secret. In 1994, the Gang of Four made a formal, somewhat academic study of this. They went out and they identified a list of about 100 patterns in most common use. They grouped them into 3 main categories: patterns to do with creating objects, patterns to do with structuring architecture, and patterns to do with behavior, with how data flows over time. And it was the Gang of Four who assigned the names to these patterns that are now standard. Many of the names were already in use, but the Gang of Four picked the ones that were going to be the standard. So since 1994, the field hasn't stayed still. There are people suggesting new patterns all the time. You will find these modern patterns. Some of those have also become very well established and canonical. So in the study of English literature, the canon is the set of great books, and people argue all the time about what should be in the canon and what should not. Or when the Bible was written, they had meetings about what should be in the canon, what should be actually put in the Bible, what should be kicked out. So the design pattern canon is behaving very similarly to that. Pretty much everyone accepts the original Gang of Four as a authoritative source of these patterns. You will see, here's a couple of examples of more recent books like Modern C+ Design. There's also a book on anti-patterns. This is a collection of specifically bad design practices, which also tend to come up all the time. So you might decide to accept the authority of books like these as well. More recently, the debate has now moved onto online forums. There are blogs, there are influencers, especially a very good software engineer called Martin Fowler, who is deeply involved in this, who tends to be considered an authority in the creation of new patterns. At the same time, some of the patterns from the Gang of Four book are maybe getting a little dated. Maybe they were all tied up with object-oriented trends in the 90s, some of which were a little excessive. So some people argue that some of those should be retired from study. So there's an ongoing debate, and there are several hundred of these patterns that everyone can at least take a look at and decide if they're useful for the work they do. So the Gang of Four have split the basic set of patterns into these three categories: creational, structural, and behavioral, which is a nice way to teach and learn by making that division. Let's take a look at creational patterns. So these are patterns to do with the construction of objects. If you're using a object-oriented language, you're probably familiar with a constructor method or function. That's the basic way of creating objects. But these are things you can do beyond that. You can create structures sitting on top of the construction method to do additional things. So a very simple pattern to begin with is called the singleton. Okay, a singleton is an object which can only have one instance. Okay, so it functions both as a class and as a single object. And you'll see the constructor in this class is deliberately set up to prevent the creation of more than one instantiation. So this is useful primarily as a contract. It's something you can tell the user of your code is going to happen. You can tell your user there will only ever be one of these, and then there are cases where that will rule out a whole load of possible bugs. If the user is looking around for the cause of a bug, they now no longer need to consider the possibility that there could be two of these objects. We often use a convention naming our variables. If you have a class cat, which you make into a singleton, the convention most people use is that when you instantiate it, you call the object the cat. So in English, the word the is the definite article. That means there's only one. If you called it a cat, that would mean there could be others. So if you see other people's code with variable names like the cat, that's a strong indication they're using the singleton design pattern, and therefore you shouldn't expect to see more than one cat in their code. So this is useful, for example, if you're doing graphics programming, your computer only has one screen, usually, maybe not always the case nowadays. You could have an object called the screen, and then that's going to guarantee that there's never going to get two of these sending conflicting information to the physical screen. If you're doing audio programming, you might only have one microphone or one amplifier and speakers to send the data to. There are many ways to implement the singleton pattern in different languages. This is the classic form. So these are UML diagrams again. We looked at these briefly before. In UML, Unified Modeling Language, we draw each class as a box. We put the class name up in the top. We put a list of member variables in the second section, and we put a list of member methods in the lower section. So what you see in the singleton class, this is a self-referential class now. The singleton has an object called its instance, and that object is used to point to itself. So when the thing is instantiated, it has a self-reference sitting in instance. And then when you call the constructor or get instance, the constructor now has some additional logic. The constructor first checks, does an instance already exist? Is there already one of me? If there is, then we're going to return a pointer to that existing instance. If there isn't an instance, then we actually create one, as in a regular constructor. And we update the instance pointer and we return a copy of that. So that's the singleton. Very, very simple, basic pattern to start with. Let's look at a few more patterns to do with creating objects. This is the prototype pattern, also known as the cloning pattern. This has actually become so common now that it's baked into several languages.
Mm.
In the cloning pattern, you would like to create new objects not by initializing them from scratch, as in a regular constructor, but by creating them as a clone of an instance that already exists. And again, we would like this to act as a contract. We would like to promise our user that this is available and that it is going to work. So to do cloning, we will typically create what is called an interface. If you're using an object-oriented language, that's a formal concept. It may exist in some languages as an abstract class or as a header file. There's going to be some form of contract, like an interface, which promises that this thing exists. So you can see here we have a prototype interface. Then we've got a bunch of classes which can implement that promise. Again, in a language like Java, you are implementing the interface. In other languages, if you're doing contract-oriented programming, they're just systems that use the contract. And that interface has promised that you will have a method called clone and that it will work to make a copy of the object. So that means that any class implementing the interface has to implement these clone methods and that it has to work. Now, cloning is not completely straightforward because when you're dealing with complex objects, they contain a mixture of actual data and pointers to other objects. And you always have to decide, if I clone my cat, am I also going to clone its ears, say? I now have two cats. Do I want them both to have a fresh copy of ears, or do I want them to share the same pair of ears and they can both just have pointers to the same object? So again, there are different conventions about this, about how it should be notated, and different arguments about what exactly cloning is. Sometimes you'll come across deep clone as a separate concept from cloning, and a deep clone is a promise that you will clone everything, so you will never have the two objects referring to the same sub-object. So for example, if you clone a cat, you'll get a complete fresh copy. You'll get a new pair of ears, a new pair of legs, new everything. And in particular, if you change one of those, then it won't affect anything on the previous cat because everything has got deep clones rather than just copying pointers across. So here's what the pattern looks like in actual code. You'll always have something like this. You'll have a class which either extends or implements or somehow says that the clone promise is getting followed. That will then force you to create a cloning method. And then inside that cloning method, you're going to construct a new cat. You're going to construct a new copy of the same class. And then you're also going to fill that clone full of copies of your stuff. So you're going to say, how many legs do I have? How many years age do I have? And you're going to copy those all over into the clone. So cloning was interesting as a pattern at the time. It's maybe become so widespread that as with everything in software engineering, so many people do it that they then start baking it into languages, and you don't always consider it as a pattern anymore. It's just becoming a language feature.
Yeah, I thought that cloning was actually separate from the idea of prototypes because JavaScript has the idea of prototype built in, and its whole instantiation and inheritance system is based off of it.
Ooh, okay.
I really don't like it because when you change the prototype, you then change how every instance of that class will now be instantiated. So I can say that any number will always return evaluate to 42 and nonsense like that. And
right,
so,
I'm not a JavaScript programmer. I'll have to go take a look at that. That's interesting.
Yeah, I thought the cloning was something separate.
Okay, cool. I'll check that out later on. Thank you. Okay, so the final creational pattern I was going to look at is called the factory pattern. This is a more complicated pattern. And the idea of this is to create objects without specifying the exact class that will be created. So many of these patterns are really intended for doing graphics. It's very common when you write a program that you have a lot of logic in your code that is to do with the application domain, and then you come along and want a graphical interface, and somehow all this graphic stuff has to talk to the business logic of what you're doing. And the aim is to not have the graphics code interfere with any of the business logic. So a lot of these patterns are really coming from this task of how do you make a whole secondary bunch of code and classes to do with graphics that is somehow going to dial into your business logic without disturbing it. So in a factory pattern, you might, for example, have written a program that has a graphics thing, and currently you request your graphics system to do something like draw a square, or in object-oriented programming, you'll request an object called a square drawer, and then you go and request a triangle drawer and a star drawer. And the problem with this is that, especially in graphics, you will often find different applications need to have different backends for doing that. So the classic example of this is found in the Cairo graphics library. This is part of GTK, used for drawing. So Cairo is designed as this very general graphics API, but inside of it there are different backends that are going to render those graphics commands either onto a screen as pixels or into a PostScript file with lines, or into all manner of other formats. You can render onto SVG files or PNG files, all kinds of things. So your user would still like to have this system where they come to you and say, make me a square drawer object, please. Make me a triangle drawing object. And your users shouldn't care how you're rendering this stuff. They don't care if you're drawing to the screen or drawing to PostScript. They just want a thing that draws triangles. So internally, you've gone off and created all these different versions. So now you've got a PostScript square renderer, you've got a PostScript triangle renderer, you've got a pixel square renderer, you've got a pixel triangle renderer, and so on. But you don't want your user to care about any of that. Your user should just come along and say, give me a square renderer. And depending on what mode you're in, if you're currently in pixel drawing mode, you're going to take that command and you're going to say, aha, here is your square renderer, and it happens to be the pixel square renderer. So that logic is called a factory. You're going to maintain a class called an object drawing factory. You're going to take these requests, like, can I have a square drawer? Can I have a triangle drawer? And then you're going to decide which subclass you're going to return. You're going to internally decide to instantiate a subclass of square drawer, which is a pixel square drawer, and that's the one that you happen to give to them. So here's a classic example of a factory pattern in Java, again written in UML. You can see here's the client. In this case, the client is asking for a product from a garment factory. Again, this is just an example, a simple example to show. And the garment factory can be previously configured to either be producing trousers or shirts. The user is just asking for product, and the garment factory will return whichever of those it's been configured for. You can see both of those are classes of garment type. So as far as the client is concerned, they're always going to get a garment type coming back. But if you're running the factory, you care about whether you're going to send them trousers or shirts as subclasses of that. So this is it's a bit of a whirlwind tour through design patterns. There are many more design patterns in all these categories. I'm just giving you a flavor of it. I'd really encourage you to read the Gang of Four book at least, and maybe look around for some modern ones as well. So the best I can do is just give you a sample of all this stuff. Those are creational patterns. Let's go to structural patterns now. So these are to do with the overall form of the architecture. What are the things being represented? How are they going to communicate with one another? Often these come up when different people have worked on different systems, and you now need to find a way to put those systems together and make everything compatible. So again, to start with the most basic, this is the adapter pattern. If you are doing anything electronic, you will already be used to physical adapters like these. These are audio and video adapters, you will just often have different creators of stuff who use different interfaces, and you need to join them together. So adapter pattern allows the interface of one class to be used as a different interface. Classic examples of this are for transporting graphics APIs, again, between different systems. So for example, we talked last week about running the GTK graphics API on Windows. Now, Windows has a native graphics API called Win32, which is full of really ugly looking commands like these. So historically, even the guy who wrote the book on this says they're ugly, right? The naming conventions use a particular form that makes everything a little hard to read. Historically, then, if you were building a Windows app, this is the API you would use. But then, since then, no one wants to write software that only runs on one company's system anymore. We want to write software that will run on anything. So we now have these separate open APIs like GTK, and then different people will come along and they will create adapters between these systems. So this is a cartoon sketch of how you would create a GTK implementation for Windows, right? This is a module. It's called GTK to Win32 adapter. And what we'll do, we'll go through all the different API calls that GTK provides, such as open a window with a name, and we will implement how you do that using the underlying Windows API. So now you can take your GTK commands and run them on the other system. Or you can, question?
I also wasn't aware that this was considered an explicit pattern. Couldn't you say that this is just a more general description of what an interface might be? So, for example, if I have some API and I write a library in some class that uses that API, wouldn't that technically be an adapter?
Yeah, right. It's a very general idea. I think with all these patterns, the way we tend to use them nowadays is to structure our own thinking about what we're doing as programmers, and that may, for example, mean going outside of one particular program or one particular language. When they were originally presented, they were more specific to work that was done within a single language, which was usually Java. So yeah, we'll see a lot of examples of this idea where if you're only implementing thing in the original Javaic style, it would only apply if everything is within a single what do you call it? A single enterprise solution where you have a bunch of classes that are all compiling together. I think the way we really use these patterns now has become more general than that. We might have things calling between languages or between systems. Sure. So yeah, the original formal version of it is expressed here in the UML. So here you've got the adaptee. Here you've got the adapter, which is wrapping it, and then here you've got the client and the target.
Yeah, and wrapper. That's the word I was looking for.
Yeah. So these in the original concept of this, these would all be classes within the same program, and they would all be compiled together. Whereas if we're taking the pattern idea in a more general sense, some of these arrows might not be things existing in the same program anymore. They might be weaker linkages between the system. Okay. So if anyone's ever used Wine, Wine is the opposite version of this. This is an implementation of the Win32 API implemented in GTK. So this is how you run Windows graphics programs on a Linux or BSD machine, for example. Wine is called Wine because it stands for Wine is not an emulator. Self-referential acronym, but this is of interest here because it is not emulating a Windows computer. It is instead giving you a different implementation of the same API, which runs directly on the new system. Okay, facade pattern. This is when you have a whole load of complex tools and libraries, and you want to provide a simple single API to your users to replace a mess of big, difficult, complex stuff. So typically to implement this, you will create a new API. That could be a header file or an interface file, whatever. Your implementation is going to call everything else. So here's your facade. This is the thing you've made. Your client, who is often, almost always, a physical human, who is asking you to make this thing. And then you're going to worry about all this complicated stuff so that this becomes your world and this becomes their world. So this is great for dealing with clients such as young children and MBAs who have difficulty with complex computational concepts. For example, Python Turtle Graphics is a lovely, it's a logo style API for drawing. It's sitting on top of all this complex stuff in Cairo and GTK. And it enables young children to write turtle graphics commands like this, moving forward, turning left, putting the pen down. You can draw very pretty pictures without having to worry about Cairo rendering surfaces or any of that stuff. If you work in corporate IT, this is probably the bulk of your life, is creating facades for people. Any corporate enterprise will have MBA types who want to do X, Y, and Z, and they don't want to learn how the stuff actually works, and so they hire you to create a facade, to make something that is much simpler for them just to interact with the business logic. Not the most glamorous work in the world. It can be quite frustrating because you will often find yourself in this position just trying to tell these guys that the stuff is already there, they just need to learn to use it. So for example, a huge portion of corporate IT consists of wrapping databases. You have an SQL database containing the actual business stuff, and your MBA types will want a nice pointy clicky graphical interface to it all that addresses only what they're interested in, and your job is to link those two things together. You're going to make this GUI facade to make it easier for the MBA to talk to the database. And it's especially frustrating. I've done this. I made some nice money out of this. That's quite a well-paid job, precisely because it is so tedious and no one else wants to do it. It's frustrating because SQL itself was designed as an easy-to-use language for business people. It was specifically written with business applications in mind. But if your client is so dumb that they can't even learn that, then you're going to have to make an even higher level facade that is so specific that they could just log in and click on some pointy clicky thing. That's the facade pattern. This is about adding functions to an individual object dynamically, as in at runtime, but without affecting the object's own behavior. So again, this is a very common thing to do with graphics or any sort of user interface. Say you have just written your wonderful music program and you've come up with a new ontological theory of the structures of musical objects, and you have a beautiful set of note classes and pitches and chords and everything. Nice, clean business logic set of code. And now you want to draw all that stuff on the screen. Now, what you really don't want to do at this point is have to go through every one of your beautiful theoretical logic-based classes and fill it all full of gunk about graphics. You don't want to take this beautiful thing describing the structure of music and just load the whole thing up with ugly GTK commands and all that stuff. That should be kept separate in another place. So graphics, one way to do this, that there are many ways to set up your graphics. A lot of these patterns are about different ways of doing it. They can compete with one another. So if you do this with a decorator pattern, one way is to extend your class or to wrap it in something called the decorator. So you might have an object like a note in your music program, and you might create this other thing called a graphical note. And your graphical note is either going to extend your note or wrap it or have a pointer to it, however you want to set this up. But it's going to sit there, it's going to be associated with the note, and it's going to provide this extra functionality, but whilst keeping it separate from the business logic of what the note was supposed to be doing in the first place. So all these graphics patterns are especially useful for human beings working in teams as well. It's very common to separate your graphics people from your business logic people. And you really don't want both of those people working on the same actual files of code if you can avoid it. You don't want everyone writing graphics code and business logic in the same class. So this is one way of keeping those things very separate. So again, here you can see an underlying component in the UML. This could be an interface implemented by a particular concrete component, and then your decorator is defined as something that sits on top of that and adds different kinds of functionality. Again, all this stuff was written in very heady object-oriented times, so you'll see these UMLs are as general as they can possibly be. They're very keen to point out that the decorator is itself an interface which could be implemented by different flavors. So you might have two different decorators which add different sets of additional functionality to the thing. This might be relevant, say, in your music program. You might want the note to play itself. Again, you don't want to fill your music logic code up with stuff about MIDI message creation. So you might have a graphics decorator and an audio decorator that are both associated with the musical note. Okay, and then we get to the bridge. Now this is here as an example of patterns getting really very fancy, arguably too fancy. Notoriously hard to explain as well. The point of a bridge is to decouple an abstraction from its implementation so that the two can vary independently at runtime. And I quoted that straight out of the Gang of Four book because it's still the best formal explanation. Okay, this sounds like total gobbledygook, right? What does this actually mean? Roughly, this is an alternative to inheritance. Normally in a object-oriented language, you'd like to have an abstraction, an abstract class like animal, and you'd like a refined abstraction like cat, which implements and extends the ideas in the abstraction. When you instantiate this abstraction will become permanently bound to its implementation. So the cat will always know that it's an animal, and it can't change that dynamically. In some cases, you might want these things to vary independently of one another at runtime, and so you have a separate system. Instead of performing inheritance, you can perform this bridging. And in bridging, you put your implementation in a completely separate class, which does not extend the original superclass. It's just a different class, and they just know about each other. You just have a pointer going from one to the other. This is actually how objects are implemented in languages like C. If you've ever done object-oriented programming in pure C, you'll see there are structs that contain pointers to their implementations like that. And again, 1990 style objects everywhere, they've made it very clear that implementer is still an abstract class and that there are different instantiations that can come out of that. So as you were asking before, this is more often seen nowadays in cases that are not all sitting within one enterprise solution compilation unit. We would more often use this idea as a general idea for our own programming design, but in a looser way than this very strict UML style classes. So for example, you could consider the language server protocol kind of as a version of this, but existing outside of a single language. So imagine the abstraction over here was a code editor, and that could be implemented by different editors like Vim or Visual Studio Code or Emacs. And then you want to have this implementation of a language server, which could be implemented in many different ways. You have a Python language server, Java language server, even different implementations of those. So there are several different Python language servers that could be plugged in. And at runtime, you want your code editor to decide which one of those implementations it's actually going to use. And you might want it to switch during runtime. You might want to have an option in your Vim to chuck out the Python backend and put in a Java backend. Now that would be very difficult to do if you had just subclassed that directly. If you built in your language server to Vim itself and you compiled Vim so that you had Python language server version of Vim as a subclass of Vim, if you wanted to set it up that way, then you would have a very hard time when your user says, please can we have the Java backend now? Because you've compiled your whole program on the assumption that you're in this subclass called Python Vim, and you'd have to destroy everything and recreate the object. Whereas doing the implementation this way, it's just making a looser connection. You've got functionality that would usually be inside the abstract class in this case, but you've deliberately taken it out and replaced inheritance with a weaker a pointer type of link. Okay, so again, LSP is a very nice example of software design. It was it was invented to solve a very common problem, which is you have X different editors and Y different backends, and every X needs to talk to every Y. And until LSP was developed, we had this horrible mess where every editor needed to know about all the different backends. So you'd have a Vim plugin just for Python, and a Vim plugin for Java, and an Emacs plugin for Python, Emacs for Java, and that held development back for a very long time. Now we have LSP. Every editor only needs to know about the LSP API, and every backend only needs to know about the LSP API. So every editor can now talk to every language server, and that's how we do static analysis now. That's how we do these drop-down menus and these auto-completions getting built into our editors. Okay, so bridge is a very strange concept to get your head around. It's really an alternative to the inheritance mechanism. Let's look at a couple of patterns to do with behavior. These are the last of the three categories coming from the Gang of Four book. So behavioral patterns are things that you do at runtime. Structural patterns are to do with the structure of the program. Behavioral patterns are to do with the execution of the program. The visitor pattern, again, very often used for graphics. This is what I did in my undergrad project, recently digging through. A visitor is something that exists outside usually your business logic. You have a bunch of classes that are all very nice, very pretty, all getting on with each other very well. And a visitor is some external thing, such as the graphics package, and it's going to dial into your business logic. It's going to look at it. It's going to inspect things, probably at every level of its hierarchy, and figure out how to do something with them, like drawing a picture of them. But it's going to do it with minimal disruption to the underlying business logic. So this is about separating an algorithm, like a drawing algorithm, from an object structure on which it operates, such as your set of musical object classes. Again, it's to avoid usually it's to avoid putting graphics code inside your business logic objects, and to make that separation of people as well as classes. So what you'll have here then, here's your client, you've got your elements. So this could be, again, this is Uber object-oriented programming. We've defined this as an interface that's going to get instantiated by a concrete element. So for example, in my code, I might call this abstract interface something like a graphical renderable entity. And my musical note is going to be implementing that interface along with a bunch of other things. So in particular, that means any object that your graphics code is going to dial into is going to provide, it's going to promise to provide one extra standard method. And here it's called accept. It's accepting the visitor dialing in. So this is a little bit of extra work for the business logic programmers. They're not going to have to write graphics code. They don't have to put GTK commands in the music object, but they are going to promise to provide you with some basic information that is essential for them to do their work. So for example, to render a musical note in Music Genie, each of these dots is a note. The note might just send back some very basic information like what are my XY coordinates and what is my color. And I'm not going to tell you how to draw those. I'm not going to do GTK stuff, but I'm just going to tell you the information that someone else needs to draw me. And then here's the visitor interface. Here's an implementation again of that interface. So in this case, it's a Java AWT based graphics rendering, which is a very, very old-fashioned Java window toolkit. It's one of the main things that's been breaking when I tried to get my project to work after 20 years. So this thing is going to be the graphics renderer. It's going to dial in. It's going to go around all the musical objects in my score. It's going to call these accept methods, and they're going to give these little bits of information like where am I, what is my color, and then it's up to the visitor to figure out how to turn that into actual graphics.
Would that be at all similar to a friend?
Sorry?
Would a visitor be similar to a friend in some applications?
To a friend? Let me think. So a friend is that a C++ concept? So
Yeah.
a friend is something that you allow into your private variables. Yeah, two classes
Yeah.
that have a kind of intimate
So
relationship.
you can see all the privates from another object.
So from design pattern school of thought, that whole idea is probably a bad idea. Just giving someone intimate access to your private parts is usually considered a bad idea. I guess the visitor pattern is maybe it's an alternative to that. Maybe this is something that was developed in response to people doing that when they shouldn't be. You can see it's doing the same thing, yeah? Very similar idea, but instead of just giving you totally unlimited access to my private parts, I'm going to define exactly what it is that you're accessing. I'm going to give you this contract, this accept method, and that's the only thing you can come in. So if you want to come and see my private parts, that's how you do it. You call this thing, and I'm in control of it. You could imagine, yeah, the friend concept is maybe it's a more low-level idea. It's just giving you indiscriminate access to everything. This is a more controlled way of doing that. Yeah.
Would
Okay,
the
yeah,
client necessarily be as a separate object, or would you need to, in some cases, have it as part of the implementation?
Again, you can probably take whatever you want from the design patterns concept. In the original formal version, it is strictly designed through this UML diagram. If you're doing what is in this UML, then that would be a gang of 4 version. But as with all the patterns, what we actually use these things for now is that more intuitive, informal design. So yeah, it's the same question, right? How formally do you want to take your design patterns concept? Okay, cool. Couple more of these behavioral patterns then, and then we'll take a break for a bit. Memento. Some of these patterns have really stupid names. They're all from a time when I was a student. It was during the dot-com era. There was a lot of money flowing around. There were a lot of trendy ideas, and Java and object-oriented programming got very big. And you'll see these kind of excessive object stars of things. So you see these stupid names. You've got an originator and a caretaker and a memento. Some of the sillier names. This is basically how you implement undo in your system. You're building a graphics program. You want to take some memento of the state it's in, and then if the user messes something up, they're going to press an undo button, and then you get back what you had before. This is not as straightforward as just taking a copy of the whole state of the image between every operation. A memento is a slightly different concept. So you have the caretaker is basically the user. The originator is the thing that is being backed up, like your image. And a memento is a separate class. It's something that you can ask the originator to give you. So you say, dear image, please give me all the information that I will need to recover your current state, as a separate kind of thing called a memento. So it's not a straight clone of the original image. It's a more general concept. It's any additional class that can be used to recover that state. So the idea is the memento could be, in many cases, smaller than a copy of the whole thing. So the workflow then is the user comes along and says, can I have a memento of the image? You're probably going to do this automatically every time they've done something. You update their memento, you say this is a record of how things were. Then you go and you mess up the originator, you draw some stupid stuff on it, and the user now comes and says, here's my memento, please can you put everything back to how it was? And you'll see these are done as contracts. They're promises that the originator is making. So the originator is promising, I will give you the opportunity to create a memento whenever you want. So the user will come in and say, give me a memento, please. And I promise I'm going to do that. And then there's a set memento method, which will take a memento that I previously made, and it will apply that to restore me to the state I was previously in. Okay, so it's not the only way of doing undo. For example, you could take a copy of the whole thing every now and again, but in some cases this is going to be useful, especially if you can find a way to make your mementos smaller and faster than doing a complete clone of the original every time. Okay, final behavioral pattern I'm going to talk about is the observer pattern. So again, very often used with graphics or any kind of media system. The idea here is that you have a subject which maintains a list of observers. You have people who are interested in the state of this object, and the subject promises to notify each of those observers whenever it changes some aspect of its state. Again, different ways of setting this up. In some cases, the subject will notify the observers when anything changes, or maybe the observers will only want to be notified when something changes. So, for example, you're building a graphical music system again. You've got your business logic representing all the musical elements like notes and pitches and chords. You've got your graphic system, and the graphic system's job is to make renderings of the business logic and to keep that rendering up to date. So if the user has changed a note in their composition, they've moved the pitch from a C to a D, the graphic system needs to know about that in a timely manner, and it needs to update the picture that it's drawing of that note to actually show it where it's gone to. Now, a stupid way to do this would be polling. You could have the graphic system just sit there, and every half a second it could dial in as a visitor, say, to the business logic and say, what's the latest state? You're going to waste a lot of work doing that because most of the time there are no changes. So what you want to do instead is have the graphics stuff register as an observer of the music stuff. And the graphic stuff is going to dial in once at the beginning and say, hello, I'm your friendly neighborhood renderer. Please let me know every time you change. The musical note, the subject, will sit there. It will keep a list of everyone who's watching it. And then whenever it changes its pitch or whatever, it will then have some extra code that calls back each of those observers and tells them that it's been updated. Okay. Again, you can have multiple observers of a single subject, or an observer could be watching many subjects. You can have fun drawing UML diagrams for all these different cases.